Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam, Doktor.
Okay, so today we will continue on our lecture regarding the PID controller. So on Monday we stopped at so tuning PID controller. So today we will look at how we can develop a PID controller for a given system by using a tuning rule. Okay, so usually the transfer function of the plant of a control system is very complicated to be modeled. Okay, so usually the plant, in ideal case, we can maybe identify the transfer function. So for example, the plant, we have the transfer function. We can identify the transfer function. But most of the time, the plant, we don't know. In real case, we don't know what is the transfer function or what is the equation of the transfer function. So it's difficult to perform analysis like root locus, Raut-Hurwitz criteria to determine the stability of the plant. And maybe we can, if we want to develop a control system, we can do experiment to determine the time response of the plant. So the tuning of PID controller, in real case, maybe we can do it by trial and error. Maybe we adjust the gains for each PID controller and to see, and then we can see whether by changing the gain, the plant or the output becomes stable. Okay. So there are persons or people that develop a tuning rules for PID controller known as Ziggler and Nicoles. So they propose rules for tuning the PID controller, which is based on the transient response of a given plant. So there are two rules, okay, two methods for Ziegler-Nicoles, and we will look at each of them one by one. Okay. So the first Ziegler-Nicoles tuning rule. So this first rule only applied for a plant that has a response to a unit step input, which has an S shape. Okay. So the response is S shape. Okay. So when you have a CT or the time response from a unit step input is an S shape, then we can use the first Ziegler-Nicoles tuning rule. Okay, so in the first rule, we need to determine two things from the time response of the given plant. So the first thing that we need to determine is this L value here, which is known as the delay time. So the delay time is the value from 0 until the point where the time response start to increase. Okay, so here is about from here from 0 until maybe about here. Okay, somewhere about here. And then the second thing that we need to know is the time constant t. So to determine the time constant t, you need to draw a tangent line at the curved part here. And then the line must intersect between this L value and also intersect with the steady state value. So the time constant is measured from the L value here until the time point where the tangent intersect the steady state value. So we need to know two things, the value of L and the value of T. So later we will do tutorial and see how we can determine this. And then from the value of T and L, we can find the transfer function for the controller using these rules, okay? Using this formula, K, the constant, the gain times E minus L times S over T times S plus 1. So this is the not controller transfer function, but this is the overall transfer function of the system. Alah, tak lengkap nota. So to find the controller transfer function, we need to find KP, TI, and TD. So KP, TI, and TD, if we use a PID controller, then we only look at this PID rows here. So to find KP, it's equals 1.2 times T over L. TI, it's 2 times L. And TD, it's 0.5 times L. And then we can use KP, TI, and TD and substitute into the controller transfer function. So the controller transfer function is tak ada. It's this one. So this is the controller transfer function. Okay. So dia dekat slide lain pula. So we find KP, TI, and TD from the table and from the graph, and then we calculate KP, TI, and TD and substitute into this transfer function. And then this will become the PID controller, and this is the transfer function of our plant. So we can simplify the system block diagram and then find the closed loop transfer function. Or actually you can just substitute K and T, I think, into here. Tapi tak ingat betul tak. Lama dah tak ajar. Okay, so let's look at an example from tutorial. Okay, so tutorial number 13. Question number 1 is about Ziggler-Nicoles first method. Okay. So the system below exhibit a time response shown by the curve under a unit step input. So design a PID controller using a suitable Ziggler-Nicoles method. So when you have the curve that exhibit S shape, then you can use first method of Ziggler-Nicoles. So the first thing that you need to determine is the value of L and then the value of T. So let's determine value of L and T from the graph. Okay, so this is your graph. So you can estimate the value of L and T. So the value of L is measured from time 0 until the moment where the curve start to rise, okay, start to increase. So maybe you can take this value, maybe until somewhere here. Okay, so if you are given graph, then you can guna pembaris measure. Okay, so this is about L equals 1 second, or maybe you can take a bit longer. Maybe measure until here pun boleh. 1.5 second. And then we need to determine the value of T. So we need to determine value of T by drawing the tangent line. So okay, that's already. Okay, so we take L equals 1 second. And then the value of T, we need to draw a tangent line, okay? So a tangent line maybe agak-agak lah, okay? So let's say somewhere here. And then you need to determine 2 intersection point. So the first one is intersection between the tangent line and the steady state value. And then the second intersection is between the value L. So the time constant T is this length, okay? So about maybe this is 3.5. So this is 1 second. So maybe about 2.5 second. Okay, so we get our L and T. Then we can determine the value of Kp, Ti, and Td. And then we can look at the table. So the third row here. So Kp equals 1.2 T over L. So you get 3. And then Ti, 2 times L. So you get 2. And then Td is 0.5 times L. So you get 1 over 2. And then substitute this into the transfer function for the controller. Okay, so transfer function for controller equals Kp times 1 plus 1 over Ti times S plus TdS. Okay, so just substitute the value that you have found. So we have 3 times 1 plus 1 over 2S plus 1 over 2S. And then you can, it's better if you can simplify this. So you get no. So you get so you can rewrite okay. So this is the transfer function for the PID controller. So basically you answered the first question, okay? So the question asks you to design a PID controller. But sometimes maybe the question asks you to find the closed loop transfer function, meaning that you need to simplify this block diagram. So to find the closed loop transfer function, so simplifying CS over RS. So you get GC S times GS over 1 plus GCS times GS. So just substitute the value from the transfer function. Okay, then simplify the transfer function. Okay, so this is the final closed loop transfer function of the system. Okay, so any question before we move on to second method, second rules? So macam surprising senangnya. Okay, memang senang pun untuk first rules. So that's why dia tak keluar final. Any question before we proceed? Okay, so if you have no question, then I hope you get the idea of how to use the tuning rules for Ziggler-Nicoles method. So you need to find T and L, and then refer to the table and use the PID controller, the row for PID controller, find KP, TI, and TD, and substitute into the transfer function of controller to get the controller transfer function. And then if the question asks you to simplify the block diagram, then just calculate as usual. Okay, so that's about the first tuning method. So first tuning method is used when you have a step response of a plant that has that exhibit as shape curve. Okay. So now we look at the second Ziggler-Nicoles tuning method. So for second Ziggler-Nicoles method, it's a bit complicated, but still easy to calculate. Okay. So firstly, we set the integral and derivative gains. So again, this is the controller transfer function. Okay, so in second Ziggler-Nicoles method, we assume that the integral and derivative gain, we set them as 0. Okay, so we set this as 0. So we only left with Kp. So the controller depends only the proportional gain. Okay, so we have only Kp here. And then from here, we can increase the value of Kp such that it becomes or it reach a value, we call it the critical gain value, KCR. Okay, so we increase Kp until we reach a critical KCR value. So this critical value is the value when the system exhibit a sustained oscillation with a period PCR. So you have a time response, you increase K, and you evaluate the time response until the time response becomes oscillating. Okay. So it oscillate with a period PCR. So if you look at this oscillation, it's similar to a system with marginally stable system. So basically what happened is that you increase K, you increase Kp until the system becomes marginally stable. So after that, you determine the value of Kp, the value of Kp that the system exhibit marginally stable system, and also determine the period of oscillation PCR. Or if you still remember Rauch-Hurwitz criteria, PCR, or you can determine the frequency, the FCR, frequency at marginally stable. Or in another language, we call it at J omega crossing. Okay, so we determine the value of Kp and frequency at J omega crossing. Okay, so we need to use route width criteria and kena ingat balik apa yang dah belajar dekat root locus. Okay, so we use the value of KCR or the KP value and PCR and substitute into this third row PID. So KP equals 0.6 KCR, TI equals 0.5 times PCR, and TD equals 0.125 times PCR. Okay, so let's look at an example. So design a PID controller for the system above using second Ziggler-Nicoles tuning rule. Okay, so you are given this transfer function and a PID controller. So you are asked to determine the controller transfer function using second Ziggler-Nicoles. So let's look how we can do this. Okay, so since the plant has an integrator, so we can use Ziggler-Nicoles tuning rules. So firstly, we assume that the value of TI and TD or the value of gain for integral and derivative are 0, okay? So we can obtain the closed loop transfer function as below. So we assume that GC is made up of only KP. Okay, so we simplify this block diagram to get the closed loop transfer function. Okay, so the closed loop transfer function is given by this closed loop transfer function. Okay, and then we increase KP, that makes the system to become marginally stable and with sustained oscillation. So we can use route width stability criteria. Okay, so we take the denominator. We take the denominator and perform and write the characteristic equation of this denominator. And then we arrange in route table, okay, or route array. So here we start at s power of 3. So s power of 3 followed by s squared. So we arrange them alternatingly and then calculate S1 using determinant and calculate S0. Okay, so then we can determine the value of Kp and also frequency at J omega crossing. Okay, so examining the coefficient of the first column, so we find that the sustained oscillation occurs at row S1, okay? So use row S1, we get Kp equals 30. So Kp equals 30 is actually the critical gain value, KCR. And then we use this Kp value or this KCR and substitute into the second row. Ataupun macam cara dia buat, dia just substitute in here. But you will get similar results, okay? So if you substitute in S2, so 6S squared plus Kp 30 equals 0. And then we can get our S equals square root 5. Okay, dari sini, so we get S equals plus minus square root 5, okay? J. And so the frequency is this. This is the frequency of the marginally stable oscillation. So from the frequency, we can determine the period of the oscillation. So period is 1 over frequency. Okay, so since this frequency is in radian per second, so we need to use PCR equals 2 pi divided by omega. So this is omega, okay, not frequency f, okay. So omega is 2 pi f. So T is 1 over omega, 1 over F, or equals 2 pi over omega. And then find PCR. So we get PCR equals 2.8099. And then we have our KP and PCR, KCR and PCR. So we can use the table, the third row here, and find KP, TI, and TD. So here, the example finds for you already. So KP equals 18, TI equals 1.405, and TD equals 0.35124. So we can use this KP, TI, and TD and substitute into the transfer function for the controller. Okay, tadi silap. Okay, tadi saya letak TI kat atas. So TI kat bawah. And then this is the transfer function for controller. So KP times 1 plus 1 over TIS plus TD times S. So substitute the value and you get the transfer function for the controller. And then you can, if the question asks you to find the overall closed loop transfer function, then you just simplify this block diagram. Okay, so let's look at an example tutorial from tutorial. Okay, so the second question is about Ziggler-Nicoles second rules. So a closed loop system is shown below. If the plant has transfer function given here, so the question asks you find the critical gain KCR when the system is marginally stable. So you have a controller with gain K, and then you need to find the critical gain KCR. So first we find the closed loop transfer function. Okay, so TS equals CS over RS. So you get K times G over 1 plus K times G. And then substitute G and K. So you get K over 2S power 4 plus 5S cubed plus S squared plus 2S plus K. And then we can take the denominator. So denominator is 2S power 4 plus 5S cubed plus S squared plus 2S plus K. And then we can generate the route table. So start with S power 4 followed by S power 3. And then arrange the coefficient alternatingly. And then find S2, S squared. So 4 minus 5 minus 1 times 1 times minus over 5. So you get 1 over 5. And then here it's K. And then find S1. So you get 2 over 5 minus 5K over 1 over 5. And then find S0. So here is K. Okay, then we can use row number 1. So use row S1 to find the value of k. So 2 over 5 minus 5k equals 0. So you get k equals 2 over 25. And then you can use row S2. Okay, ini soalan obviously soalan B lah. So before we find for row S2, so this is the critical gain for marginally stable system. Okay, so this is the answer for question A. Okay, so maybe in exam, if you are asked to find KCR for marginally stable system, so don't stop here. So please mention that this is the KCR. Okay, some student they forget to write this thing, so hilanglah satu markah. Okay, so please state that this is the KCR value. Maybe you find KCR, but you are so eager to find the frequency until you forget to write this. Okay, so please make sure you write this. And then question B, design a PID controller using suitable Ziggler-Nicoles method for the above system. So we have KCR. So to design PID controller, meaning that we need to find PCR. So here use row S2 to find the frequency for the marginally stable system. So use row S2, you get 1.1 over 5 S squared plus K equals 0. And then substitute the K value. So 1 over 5 S squared plus 2 over 25. And then S squared equals minus 2 over 5. So S equals J omega equals about 0.6325 J plus minus. So the frequency is 0.6325. So we need to find the period of oscillation. So period PCR equals 1 over FCR. So this is CR. So 1 over FCR equals 2 pi over omega CR. So substitute this value. So you get a period of about 9.934 seconds. So we get PCR and KCR. So our KCR just now is 2 over 25. So we can use the table to find the PID controller gains. So KP equals 0.6 KCR. So you get 0.24. And then TI 0.5 PCR. So you get about 4.97. And then TD about 1.242. So we get this value, then we can substitute into the transfer function here. So the controller transfer function is KP times 1 plus, yes, ada soalan?
So yang saya cakap guna table tu dekat mana?
Table PID ke?
Ada saya cakap guna table tadi. Table yang ni.
Yang ni.
Macam mana kita nak tahu nak kena ambil baris mana satu sir?
Sebab soalan dia selalu design PID. So kita ambil PID controller. Jaranglah
Oh,
dia tanya design PI. Tak tanya, dia tanya PID. Selalu PID je.
okey sir.
Okay, so tak ada lagi soalan P and PI. Okay, so we only ask PID. Okay, so substitute into this GC, the transfer function of controller. So just try to simplify. Okay. Okay, ni nak simplify pun entah. Okay, so try to simplify, but my answer I don't simplify. Okay, so this is the transfer function for the controller. So sometimes they will ask you to find the closed loop transfer function for the overall system, and but most of the time the question will not give you GS. Okay, will not give you the transfer function for the plant. So maybe instead of giving you the transfer function for the plant, maybe the question asks you to find the transfer function of the plant first. Okay, maybe it will give you a system, maybe gearing system, maybe translational mechanics system or damper system ke, so that you find the transfer function GS first. So after you find transfer function GS, then you can find the KCR value and PCR value, and finally find the controller transfer function. Okay, so this example only shows you how to find KCR and PCR. Okay, so that's it for this lecture. Okay, so that's it for control system, automatic control. Dah habis dah. Okay, any question before we finish our class for this semester? Oh, lupa exam. Okay, exam, final exam. So your final exam, it's 60%. Okay, so 60%. So there are 4 questions. So as usual, 4 questions. So each question will be 25 marks. Okay, so the final marks will be 100% and then converted to 60%. So basically one question is about 15 marks. Okay, 15 marks for your overall marks. So 4 question. I think question 1 is about basic control system. Back to lecture 1, and then maybe about translational mechanics, and then Laplace transform, and also steady state error. Steady state error. Okay, so there are 4 things in question 1. And then question number 2, I think it's about block diagram reduction. And root locus. And question 3, um, lead compensator. And question 4 is about PID controller and gearing. Okay, so this is the topic that will come up in your final exam. Okay, so final exam is 60%. So whoever thinks you can excel in final exam, you get 60% over 60. You don't have to do your quiz and your project. Okay, but whoever wants to score in AC, please do your project number 2, and your quiz. Okay, quiz number 5. We still have quiz number 5. Maybe will be given to you. I think end of this week. Okay, inshallah I will ask Cik Rosmazi. So please do your quiz and project as best as you can. Okay, so that you can get maybe 30% from your carry marks. Because in final exam maybe ada susah ke, maybe ada masalah ke, so you cannot get much marks for your final exam. So please do your project and quiz the best as you can. Okay, so maybe your midterm marks last time, your quiz and project for midterms is not very good, so please do the best for your quiz number 5, and number 4 already submitted, and your second part of project. Okay, so any question before we end this lecture?
Sir, yang gearing tu apa sir? Yang untuk question 4.
Gearing mechanical system. Lecture berapa tah? Lecture 4 kot.
Okay sir.
Okay, so before we end, I want to promote about FYP. So I'm looking for FYP student for next semester. So if you are interested to do FYP under my supervision, and my research topics is in biomedical engineering simulation. So it's about simulation. So we are going to use finite element method software. So I'm going to use COMSOL multiphysics software or MATLAB, and maybe there will be some calculation, maybe a very small amount of calculation. But if you are interested to use software, then maybe this topic is suitable for you. So my research topic is about CFD analysis in our heart or in blood vessels. So we do simulation about heart and also blood vessel. And also we can do modeling of the heart involving multiphysics. So our heart has blood flow, and also it's keep contracting. So we can do simulation how to see the heart contracting, okay, using finite element method. So we call this multiphysics. And if you are interested to know more about AI or deep learning, so I'm also do a project on image analysis using AI and deep learning. And that's it for this subject. Any question that you want to ask, maybe about your project, about your quiz, or maybe your final exam, or any question regarding tutorial, you can just text me through WhatsApp, or kalau prefer email pun boleh juga. Tapi please do not hesitate to ask me if you have any question that you want to ask. Okay, so that's it for this lecture. See you again, inshallah, maybe in any other courses next semester. So thank you. Goodbye. Assalamualaikum.
Thank you sir.
Thank you, sir.
Thank
Thank
you.
you, sir.
Thank you, sir.
Thank you, Doctor.